Hello everyone, welcome again to EGN 3343 Thermodynamics, and today we're going to go over more vapor power cycles. Last class we introduced the basic Rankine cycle as the most standard way of producing power by with vapor, in particular with steam, superheated vapor, superheated water. Today we're going to look into a couple of modifications that can be applied or implemented into these Rankine cycles, and with the sole purpose of actually increasing the efficiency, the total power efficiency at the end of the process, or the total efficiency of the cycle. We found that in the example we worked out under the conditions and state and properties, we found that the basic power cycle that we analyzed yielded an efficiency of about 39.7%. That is assuming that the devices were ideal, that the adiabatic devices were ideal, such as the turbine had 100% efficiency and the pump had 100% adiabatic efficiency. Once we included the efficiency of those devices, the overall cycle efficiency went down to about 31%. But the ideal basic Rankine cycle yielded an efficiency of about 39.7%. Now let's see what these modifications to the Rankine cycle will actually benefit in terms of increasing efficiency. There is a few modifications that can be performed to the basic Rankine cycle, and as I said, with the sole purpose of increasing the overall cycle efficiency. In our basic Rankine cycle example, we observed that the thermal efficiency was about 2/3 of the maximum theoretical, or the Carnot efficiency. Now let's examine some ways we may improve this efficiency. These different modifications include reheating, taking part of the vapor out of the turbine and passing it through the boiler again so that we can reheat it before expanding it further in the turbine. We can regenerate, which means we can combine part of the cold water with the hot water before it goes to the boiler, so that when it enters the boiler it's not that cold, so it has already some enthalpy content, so it's actually cheaper to heat up. There's a closed regenerative type of modification to the Rankine cycle, which is the same concept of regeneration but using a closed feed water system. And there's a combination of reheat regenerative, and there's many other types of modifications to the basic Rankine cycle, but in particular we are going to study the two most common ones, the reheat and the regenerative type of modification. Let's look at the reheat Rankine cycle first. In the reheat Rankine cycle, instead of expanding to condenser pressure in one pass through a turbine, what we do is that we expand only part way in a high pressure turbine, then take the steam back to the boiler and reheat it before it goes to another turbine, a low pressure turbine. So we basically have two turbines in series. The first turbine will lower the pressure to an intermediate one, and then what comes out of that turbine is passed again through the boiler. Then whatever comes out of that boiler is passed to another turbine, which expands the steam to the lowest pressure in the system. So this is what the schematics of a reheat Rankine cycle will look like. Same thing, point one, or state number one, is at the inlet of the pump. Then it's actually compressed adiabatically in the pump to a high pressure. Then it's passed through a boiler. In the boiler, the enthalpy of the water is increased by creating superheated vapor, and it is passed through a high pressure turbine, where the pressure of the steam is reduced, but it's reduced to an intermediate value, taking out of that high pressure turbine, passed through the boiler, and again to increase its enthalpy, and then passed again through a low pressure turbine that will expand the vapor to the lowest pressure in the system. Okay, so now we have two turbines in series, a high pressure turbine and a low pressure turbine. So we'll essentially be creating more power, but at the same time we'll actually be investing more fuel, because we'll be passing the steam twice through the boiler. So the QN, the cost of the cycle, the denominator of the efficiency, will be higher. The numerator will be higher, but the hope is that the increase in that numerator will actually be larger in proportion than the increase in the denominator, so that these modification yields a slightly higher efficiency than what we have found before. So then at the exit of the low pressure turbine, as always, the steam, or the mixture, the wet vapor mixture that comes out of the low pressure turbine, is passed through a condenser so that we can obtain saturated liquid that can be used in the pump back into the boiler. Now, if you look at this in a TS diagram, remember from 1 to 2 is what happens in the pump. And this is an isentropic compression or an isentropic increase in pressure. Then it's passed through the boiler from 2 to 3, in which at constant pressure, notice that this is going through an isobaric line. Through an isobaric line from 2 to 3, the temperatures increase in order to make superheated vapor. Then the first turbine expands through point 4s isentropically. It can expand enough to go into the saturation dome or to stay outside, depending on the conditions, depending on what that first expansion pressure is like. Then it is passed through the boiler again, and as you can see, at constant pressure from 4 to 5, the temperatures increase and it's taken back into the superheater regime. Then from 5 to 6 is another expansion in the low pressure turbine this time. It is going to go from this pressure to this pressure. Notice that the system now operates between 3 pressure, the high, the intermediate, and the low pressure. 3 isobars. Point 6s is the isentropic expansion point in the low pressure turbine from 5 to 6. And then from 6 to 1 is taken to the condenser, which is the heat rejection process. It's the process of cooling the water. In this case, cooling doesn't necessarily mean lowering the temperature, because notice that the temperature remains the same, but it's basically changing its phase from wet vapor all the way down to saturated liquid, so that it can be passed through the pump and sent back to the boiler. Now, notice now that the process in the boiler have changed, because we have 2 passes through the boiler. We have the point 2 to 3, or the process from 2 to 3, and we also have the process from 4 to 5 going through the boiler. And if we apply the first law of thermodynamics to this boiler, that has 2 inlets and 2 outlets, we'll notice that by eliminating all the negligible terms, which include the kinetic energy changes and the potential energy changes, we'll find that Qn, which essentially is Q from 2 to 3 and Q from 4 to 5, is delta H from 3 to 2, or from 2 to 3, and delta H from 4 to 5. So it's a change in enthalpy from point 2 to point 3, and the change in enthalpy from point 4 to point 5. Since it is the same mass flow rate that goes from 2 to 3 that it goes from 4 to 5, because remember, this is going through a turbine, and we're extracting all of the steam out of the turbine and passing it again through the boiler. So the mass flow rate from 2 to 3 is exactly the same as the mass flow rate from 4 to 5. We've divided everything by mass flow rate and left these in specific form. So this is the Qn. This is what goes in the denominator of the efficiency. Now notice this Qn is larger than before because we have an extra pass, this enthalpy increase from 4 to 5. Then we can apply the first law of thermodynamics in the turbines. Now we have 2 turbines. We have a process from 3 to 4, and we have a process from 5 to 6. Both processes are ideally isentropic. This is an isentropic expansion. In reality, it's just adiabatic expansion, but ideally it's an isentropic expansion. So we can apply the first law of thermo on the high pressure turbine, the first law of thermo on the low pressure turbine, add the 2, and that will be the positive work. We subtract that, we take the work out of the pump away from this, and that will be the net work. So in theory, we produce more work in the reheat cycle. If we apply the first law of thermodynamics, the work on the turbine, the overall work on the turbine will be the work in the high pressure turbine, which is minus delta H from 3 to 4, and the work in the low pressure turbine, which is minus delta H from 5 to 6. This is the total work in the turbine. And at the end, we have the work in the pump being minus delta H from 1 to 2, which can always be reduced to or basically simplified as specific volume times the change in pressure. Qn is the change in enthalpy from 2 to 3 and the change in enthalpy from 4 to 5. The work in the turbine, which is the turbine of high pressure and the turbine of low pressure. And the Q out, if it's necessary, is the Q rejected in the condenser. And these are all the quantities that are necessary in order to analyze the complete cycle and calculate the cycle efficiency. All right, now let's work on an example of a reheat Rankine cycle and see what type of efficiency increase we find as compared to the basic Rankine cycle. Now in this case, we have exactly the same conditions. We have superheated vapor coming out of the boiler at 80 bar and 480 Celsius. So we achieved the same exact conditions that we've achieved in the example before. However, that is passed through a high pressure turbine. And then whatever comes out of the high pressure turbine is passed again through the boiler at 7 bar. So the first turbine actually reduces the pressure from 80 bar to 7 bar. And now when it passes again through the boiler, it's increased to 500 Celsius. The condenser pressure, which is the pressure that comes out of the low pressure turbine, is the same as before, 0.08 bar. And the net power output of the cycle is 100 megawatts. That's the net specific work times the mass flow rate. And we're being asked exactly the same things. The Carnot efficiency, the thermal efficiency. The thermal efficiency, if the adiabatic efficiency of the pump and turbines are 0.7, 0.8, and 0.8 respectively. So that means the efficiency of the pump is 70% and the efficiency of the two turbines is 80% and 80%. And we are to calculate that efficiency of the cycle in that case, with the cycle not being ideal. So let's look at the summary of given conditions. Now we have 6 states in the entire cycle. One is usually, as always, the pump inlet. The inlet of the pump is at 0.08 bars, and the pump actually increases the pressure to 80 bars. What comes into the pump is perfectly saturated liquid, quality of 0, because it comes directly out of the condenser. It goes into the turbine, the high pressure turbine at 80 bar and 480 Celsius, because that's what comes out of the boiler, and it leaves that turbine at 7 bar. It goes again to the boiler at 7 bar and it comes out at 500 Celsius, and then it comes out of that turbine at 0.08 bar. So the low pressure turbine expands the vapor from 7 bar to 0.08 bar. That's the condenser inlet, and the condenser outlet, which obviously occurs at constant pressure, is saturated liquid. That's why it's called a condenser. Now let's look at the states that we have enough information to complete. We have enough information in state number 1 because we have quality and pressure. We have enough information in state number 3 because we have pressure and temperature. And we have enough information in state number 5 because we have pressure and temperature. As long as we have 2 things, we have enough to complete the entire state. That means finding enthalpy and entropy. So let's see. At a pressure of 0.08 bar, the saturation temperature is 41.51. The saturated liquid volume, if we need the volume, is this much. The saturated liquid enthalpy is 173.88, and saturated liquid entropy is 0.5926. Those are the conditions at the inlet of the pump. At 7 bar, the temperature saturation is 165 Celsius. We are being told that the reheat occurs at exactly 500 Celsius. When it's passed again through the boiler, it's 500 Celsius. So that reheat is obviously superheated. At 7 bar and 500 Celsius, this is the enthalpy and this is the entropy. 3481.7 and 792.99. And we also know that at the first pass through the boiler, the pressure was 80 bar, which is the pressure at the pump, at the outlet of the pump, and is passed through the boiler and heated to 480 Celsius, which is superheated, as you can see, with an enthalpy of 3348.4 and an entropy of 6686. Let's bring those numbers back into the table. As you can see, we completed state number 1 at a pressure of 0.08. Since we know the quality, we know this is in saturation. Actually, we know it's exactly on the left line of the saturation dome. But the temperature is the temperature of saturation, 41.51. Enthalpy is 173.88, and entropy is 0.5926. At point 3, it's the first pass through the boiler. Pressure is 80, and temperature is 480. We know this is superheated, that's why there's no quality. 3348.4 is the enthalpy, and the entropy is 6.6586. And at the second pass through the boiler, after the second pass through the boiler, pressure is 7. Temperature is 500. This is superheated, as we found on the saturation tables. Enthalpy is 3481.7, and entropy is 7.9299. Now, according to the ideal reversible processes in the pump, in the high pressure turbine, and in the low pressure turbine, the entropy is maintained. As long as you assume ideal, a reversible process from 1 to 2, from 3 to 4, and from 5 to 6. That's why I now call these states 2S, 4S, and 6S, because these are the isentropic states. So I am copying the entropy from state 1 to state 2, from state 3 to state 4, and from state 5 to state 6. Notice that for the value of the quality at point 2, I wrote CL, which is compressed liquid. There's no quality outside the saturation dome. It's not defined. And in state 3 and in state 5, I wrote SH for superheated. The temperature 0.2 is slightly higher than the temperature 41.51, but it's negligible. We don't need to calculate it. Actually, we don't even need to go into the compressed liquid tables. Remember that we are going to approximate the power generated, or the power used in the pump, as the change of pressures times a specific volume. The specific volume of liquid water is 10 to the minus 3 meter cubes per kilogram. So, how do we find out about state 2s? Well, it is compressed liquid in state 2. We know that the enthalpy of state 2 is given by the pressure of 80 bar and the known entropy of 0.5926. But instead of trying to go to the table at that pressure and that entropy, let's not use the compressed liquid tables because they're very limited. And as always, let's approximate the work from 1 to 2. Instead of as minus delta H, it's going to be specific volume times minus delta P. Specific volume of liquid water, always 10 to the minus 3 meter cube per kilogram. And the change in pressures is 0.08 bar at the inlet and 80 bar at the outlet. Obviously, we're going to obtain a negative work because the pump is work on the system. The conversion between bar and kilopascals is 100 to 1, and that will actually make it possible for these to be kilojoules over kilogram. So the work in the pump, the ideal work in the pump, is minus 7.992 kilojoules for every kilogram of water that passes through it. That's the ideal. In reality, that pump will require more work, okay, because of its adiabatic efficiency. So with this value, we can calculate the enthalpy at the exit of the pump, or at the inlet of the boiler. Work from 1 to 2 is H1 minus H2 through the first law of thermodynamics. So we can solve for H2S as H1 minus W, and that would be 181.87. So the water goes into the pump at 173.88 and comes out of the pump at 181.87. How about state 4? State 4 is after the pass through the first turbine, the high pressure turbine. It goes in at 80 degrees Celsius and 80 bars and 480 Celsius, and then it comes out at 7 bar. Ideally at the same entropy as what it comes in with. So it comes in at 6.6586 and it comes out at 6.6586, ideally. So at 7 bar, the entropy of saturated liquid and saturated vapor are 1.99 and 6.7 respectively. So that means that this value of entropy for state 4 is in between these two. That means that state 4 is wet vapor. It's inside the saturation dome. State 4, or at least the ideal state 4S, is somewhere inside the saturation dome. And if we use these values to calculate the quality, we get 0.9895. So it goes from superheated vertically down to, it crosses the right line of the saturation dome, but it crosses it slightly to almost 99% quality. So it's very, very close to the right line of the saturation dome. Then with this quality, we can calculate the enthalpy of state 4, which is the enthalpy of 7 bar and a quality of 0.99 or 0.9895. Given the enthalpy of saturated liquid and the enthalpy of saturated vapor, we plug it into the equation for enthalpy at 0.4 is equal to enthalpy of saturated liquid plus quality times enthalpy of saturated vapor minus enthalpy of saturated liquid, and we find it to be obviously very close to Hg, 274187 kilojoules per kilogram. That's the enthalpy of 0.4, at least the ideal one, because we are assuming that the process from 3 to 4 is isentropic. And the same thing goes for 0.6s. And 0.6s, which is the ideal outlet of the low pressure turbine, is 0.08 bar and the same entropy as 0.5, the same entropy as the inlet. If we compare that entropy to the entropy of saturated liquid and vapor at 0.08 bar, we'll notice that it's in between. And being in between means that state 6 is wet vapor. Then we can calculate the quality, and the quality turns out to be 0.96. Now we're farther inside the saturation dome. Okay, it's 7.9299 minus 0.59 divided by 8.22 minus 0.59. So it's 96.09%. Again, at 0.08 bar, which is the pressure at the outlet, 0.6, we have the enthalpy of saturated liquid and the entropy of saturated vapor. We plug those values into the equation with the new quality, and we get 2,482.95. So now we have all the enthalpies, 0.2, 0.4, and 0.6, at least the ideal ones. So all we have to do is plug them back in the table. Now we have all the enthalpies in the table, and remember, for the analysis of a Rankine cycle, that's all we need. All we need is all the enthalpies and all the states in the system. Because applying the first law of thermo will get us what is the Q in, what is the Q out, what is the W. All we need is the enthalpies. But these are the enthalpies for the ideal cases. Notice that I wrote 2S, 4S, and 6S. Let's go back. Work on the pump. We already found it to be minus 7.992. Okay? Or we can just subtract H1 minus H2, minus delta H from 1 to 2. The Q in the boiler, at least the first pass, is the enthalpy change from 2 to 3. In the case of the ideal pass, we get a Q in of 3,166. The second pass through the boiler is the change in enthalpy from 4 to 5. That's 739.83. So that's the additional cost associated with reheating the vapor. So there is an additional cost because you're passing water back through the boiler, which is going to cost you in terms of burning fuel in order to increase this much energy in that water. However, by investing in this additional work and this additional heat, we are creating additional work because we have two turbines. The first turbine, which is the high pressure one, goes from 3 to 4 and it generates 606.53 kilojoules per kilogram. And the other one generates 998.75. That's the low pressure turbine from 7 bar to 0.08 bar. And the heat rejected, only occurring at the condenser, is delta H from 6 to 1, or H1 minus H6. And there's a rejection of minus 2,309. Now remember that in cycles, whether this is open system or closed systems, the net amount of work is equal to the net amount of heat. So if you add all the heats, Q at the boiler, Q at the other boiler, and Q at the condenser, if you add them all with their respective signs, you get about, in this case, 1,500. Add this one plus this one and subtract this one, you get about 1,500. And then if you add all the networks, you get exactly all the works in the system, which is the work on the high pressure turbine, the work on the low pressure turbine, and the work on the pump. Two of them positives and one negative, you get 1,597. The net amount of work equals the net amount of heat. Now with the specific work being calculated, the net specific work, 1,597.29 kilojoules per every kilogram of water that passes through the system, we can use that to calculate the mass flow rate that's necessary in order to create 100 megawatts of power. We're told that this power plant generates 100 megawatts of power. Remember that power is equal to mass flow rate times specific work. So we can calculate the mass flow rate as power divided by specific work. So this means that we need 62.61 kilograms per second of water passing through the system in order to generate, under these conditions, 100 megawatts of power. The other question in the problem is the amount of heat that is added to the water. Well, the amount of heat in the boiler, heat in the form of energy rate, is equal to the mass flow rate times Q in. The mass flow rate that we found was 62.61, and the Q in is the Q in the first pass of the boiler plus the Q in the second pass of the boiler. That means that the amount of energy added to the water is 244 megawatts, or 244,000 kilowatts. So we invest 244 megawatts of energy in the form of heat by burning fuel in order to produce 100 megawatts of energy in the form of mechanical energy, rotating power, in order to produce electricity and a generator. Okay. So the cycle efficiency, the efficiency of Carnot, the ideal one, is 1 minus the coldest divided by the hottest temperature. Remember, always in Kelvin, absolute temperature. The coldest temperature is 41.51. The highest temperature is after the second pass of the boiler is 500 Celsius. That is about 59.31%. The efficiency of the cycle is the net amount of work divided by the Q in, which can be done in rate form or in specific form, because at the end you're going to get the same. The net amount of work is 100 megawatts, or in specific form 1597.29. And Qn is 3,906.36, which is the delta H after the first pass of the boiler plus the delta H after the second pass of the boiler. And that yields an efficiency of 40.89%. That is about 1.2% higher than the efficiency that we found with the basic Rankine cycle. By adding this reheat process to the cycle and making it a reheat Rankine cycle, we increase the efficiency about 1.1%. Is that worth it? Is it worth doing all this investment of adding this reheat cycle and the additional piping and the additional losses in order to increase the efficiency by only 1.1%? Well, don't think about 1.1%. Think about the energy cost. Remember that you're putting in 244 megawatts of heat by burning fuel. If you increase 1% of 244 megawatts is 2.4 megawatts or 2.5 megawatts. 2.5 megawatts of power is a lot, and that's exactly what you're saving by this increase in efficiency. This can be actually millions of dollars a month or even a day, depending on the amount of power that you're using or producing. Okay? All right, now let's see what happens when you include the irreversibilities in the pump and in the two turbines. We found the efficiency to be 40 point some percent when the cycle is ideal. It's a reheat cycle, but it's still ideal because we're assuming that the pump and the two turbines are perfect, are perfectly isentropic. But we're told that the two turbines have an efficiency of about 80% and that the pump has an efficiency of about 70%. Which means that if the efficiency of the high pressure turbine is 0.8% or 0.8, meaning 80%, that the real work produced by the high pressure turbine will be 80% of what we found the ideal one to be, or 485.22. That also means that at the outlet of the high pressure turbine, the entropy will no longer be the isentropic entropy, because the entropies will not be the same from inlet to outlet. But we can calculate H4, we can solve it by saying from the first law of thermo that the work from 3 to 4 is equal to minus delta H from 3 to 4. So we can find H4. And H4 now, the real one, is H3 minus the actual work in the turbine. So the entropy at point 4 is 2,863.18. We can do exactly the same with the low pressure turbine. We found before that the low pressure turbine was producing 998.75 kilojoules per every kilogram of water that passed through it. But with an efficiency of 0.8%, the real amount of work that it produces is 799 kilojoules per kilogram for every kilogram of water that passes through it. Through the first law of thermo, the work from 5 to 6, no longer 5 to 6s, but 5 to 6, is minus delta H from 5 to 6, which means that we can calculate H6, and H6, or the entropy at the outlet of the low pressure turbine, is now 2,682.7. So we found the new works, the new entropies, and the same thing we can do for the pump. Now remember, the adiabatic efficiency in a pump is defined the other way around. It's a reciprocal of the efficiency of a turbine, because in a pump, the ideal work is less than, in magnitude, than the real work. So it is ideal or isentropic divided by real. Okay? Remember that when you define efficiency, you always want the bigger number in the denominator so that this yields a number that is less than 1. We're told that the pump has an adiabatic efficiency of 0.7%, so there's some irreversibilities. This means that this pump doesn't require, which ideally we found that require 8 kilojoules per kilogram of power of work. It actually requires 11.41. So it requires, in reality, more than what it ideally does. So using the first law of thermo, work from 1 to 2 is equal to minus delta H from 1 to 2. We already found that out. We can solve for H2, and that would be 185.3. It would be H1 minus the work on the pump, which is negative, so that's minus is plus, 185. Remember that in a pump, the entropy of the working fluid increases because we're increasing the pressure. So now we have all the new entropies at 4, at 6, and at 2. And then we load the table with the new values of entropy. Notice that the entropy is not copied from point 1 to point 2, from point 2 to 3 to point 4, from point 5 to point 6, because these processes are no longer isentropic. Now we have the new entropies, so we can calculate net work, and we can calculate Qn. Qn, remember, The first boiler from 2 to 3, the second boiler from 4 to 5. So the work of the pump, which is now minus 11.417, which we just found. The work on the high pressure turbine after applying the efficiency is 485.22, and the low pressure turbine is 799.0. But what's more important is the QN, which is the Q of the first pass of the boiler and the second pass of the boiler, which is 3,163 on the first pass and 618.52 on the second pass. It is almost the same thing as before. So the investment is almost the same, even in the real case. You actually have to use the same amount of fuel, but the work net is considerably less. The net amount of work, which is the sum of all the works in the process, 485 in the high pressure turbine, 799 in the low pressure turbine, and minus 11 in the pump, yields 1,272 as opposed to 1,590 something before. So this is considerably reduced. Not only that, because this system is producing less amount of net specific work, if we wanted to produce the same 100 megawatts of power, this means that this will require 78.57 kilograms of water for every second. So we need to circulate more water through the system in order to be able to produce as much power. Before we found this to be about 62 or something like that. And the amount of Q, because of this amount of power, the power is the same, 100, but because of this amount of mass flow rate, the QN is 297 megawatts as opposed to 244. So the cost of heating this vapor is much more due to the inefficiency. If we plug this back and calculate the cycle efficiencies, well, the efficiency of Carnot is the same because the temperatures haven't changed. Lowest temperature in the system and the highest temperature in the system haven't changed. What have changed now is the overall efficiency because of the irreversibilities in the pumps and the pump and the turbines. The net amount of work, which is still 100 megawatts, or now in specific form of 1,272, and the QN is 3,781, yields an efficiency of about 33.66%. Considerably less than the 40.7% that we just found, so it's 40.8%. So it's about 7% less efficiency in the overall cycle and the transformation of energy due to the irreversibilities in the pump and in the turbines. Okay. Now, but this is still higher than the efficiency that we found for the standard or basic Rankine cycle when we included the irreversibilities in the turbine and in the pump. In that case, we found about 31 point something. Now we found 33 point something. So the efficiency has now increased by 2% by just adding the reheat into the picture. Now if we plot this in the TS diagram, notice from 1 to 2 we have the pump, but that's the process 2S. Isentropically it goes vertically up, but in reality entropy increases. Entropy always increases in adiabatic processes, real adiabatic processes. Then from 2 to 3 it is actually heated up isobarically, constant pressure. From 3 to 4, isentropically it goes to 0.4 S, but in reality it goes to 0.4, which is right here. There's a slight increase in entropy. Then it's superheated again in the boiler to 0.5, and then it's expanded adiabatically to 0.6, isentropically to 0.6 S, adiabatically to 0.6. And that concludes the cycle. The cycle is closed in the condenser, where it's actually where saturated liquid is created by rejecting heat. Okay, so this is the concept of reheating the water vapor and the Rankine power cycle, and this is how we analyze a power cycle and how we found the cycle efficiency. And we demonstrated that for the same type of conditions, the overall cycle efficiency actually increases, which is what we expect out of these modifications. Now, the second type of modification that we will implement to the Rankine power cycle is regeneration. Now, in regeneration, the whole purpose is to try to save some money. It's try to save some money into heating the water vapor. And in order to do so, what we're going to do is preheat the water that goes into the boiler so that it goes to the boiler a little bit heated up so that we don't have to burn as much fuel in order to get it to the point where we want to. Okay, so what we do in order to do so, a portion of the total flow is extracted from the turbine at an intermediate pressure and used to preheat the feed water before it goes to the boiler. So we preheat the water before it goes to the boiler. This is the basic schematics of a regen Rankine cycle. As always, point 1 is the inlet of the pump, which is saturated liquid, and then it goes through the pump isentropically, ideally isentropically, to point 2, and it goes into the boiler. There's a single pass through the boiler. Now, what we want is that point 1 to be a little hotter than before. And in order to do so, we are going to mix it up in an open feed water heater with some of the water that comes out of the turbine and some of the water that comes out of the turbine at an intermediate stage. So notice that as soon as it comes out of the boiler, it's passed through the turbine, but the turbine has one inlet and 2 outlets. It has one outlet at an intermediate pressure and an outlet at a final pressure. So it's pre-expanded to an intermediate pressure where it's going to be passed through an open feed water heater. Remember, an open feed water heater is a heat exchanger where the fluid, the cold and the hot fluid actually mix in order to form, in this case, saturated vapor or saturated liquid at that pressure. So it is saturated liquid at a slightly higher pressure because this is a high pressure pump. Now this process or this system has 2 pumps and a single turbine. Now the final exit of the turbine, the vapor that comes out of the turbine, usually wet vapor, is passed again through a condenser the same way, and then the condenser saturated liquid is created. It's passed through a low pressure turbine in order to match the pressure of the open feed water heater, because remember that all streams going in and out of the open feed water heater have to be at exactly the same pressure for this system to operate. So the pressure at 4 is the same pressure at 7, which is the pressure that comes out of the low pressure turbine. Then they mix up in this chamber, they come out to the high pressure turbine, which when there is compressed again to the highest pressure in the system. So this system operates between 3 pressures. Now if we analyze every one of these steps in particular, notice this is a TS diagram of the whole system. From 1 to 2 is the compression on the high pressure pump, which goes from the intermediate pressure to the high pressure. Then from 2 to 3 is the heat added in the boiler. Notice that this heat added is smaller because it's not added all the way from down here, but it's added from 2 to 3. Okay, so the heat added in the boiler is the heat from 2 to 3. That's heat in. Then it's expanded in the turbine isentropically, ideally isentropically, to 0.4, which might be inside of the saturation dome or just outside, but it's vertical, and to 0.5, to the intermediate and to the low pressure. Okay, and that occurs within the same turbine. And then from 0.4 to 0.1 is the open feed water heater, and as well as 0.5 goes into the condenser, and into the condenser, out of the condenser as saturated liquid, then into the low pressure pump. And as it comes out of the low pressure pump, it meets at this 0.1, which is the exit of the open feed water heater. So the open feed water heater is represented by the exit of the condenser and the outlet of the intermediate turbine. And it exits from the open feed water heater into the high pressure pump in order to go back into the boiler. Let's analyze what happens in the open feed water heater. And remember, when we started devices and open system devices, open feed water heaters are adiabatic devices. There's no heat that escapes the walls or the boundaries of the open feed water heater. All the heat exchange takes place within the streams that go in and out of the system. So Q and W vanish in an open feed water heater. There is no Q that goes in or out of the system, and obviously there's no shaft, so there's no W. If you do a mass analysis, mass conservation analysis, a continuity equation, the mass flow rate that comes out, which is mass 1, is equal to the mass flow rates that go in, which is 4 and 7. And if you do a first law analysis, first law of thermoanalysis, Q minus W is equal to the mass flow rate times the enthalpy coming out minus mass flow rate and times the enthalpy of all the inlets, okay, which is M4H4 and M7H7. Now these are different from each other, but we know that this one plus this one is equal to M1. Let's go back to the overall circuit and notice that the entire mass flow rate, which is 1, 2, and 3, is broken up in 2 pieces. One that goes through 4 and one that goes through 5. The one that goes through 5 is the same that goes through 6, through 7, and then it's mixed again in the open feed water heater to form the entire mass flow rate. So the entire mass flow rate value, M1, M2, and 3, is broken up into M4 and M5, and then mixed up again in the open feed water heater. So now we have to worry about the issues of mass flow rate and this division of the mass flow rate. In the open feed water heater, we extract M4. In the turbine, that is. Let's go back. We extract M4. This is what we call the turbine extract. That's the intermediate value at an intermediate point in the turbine. We extract some of the mass flow rate. It's a proportion of the mass flow rate extraction at the intermediate stage of the turbine. And let's define Y as the fraction of extraction from that turbine. So it is M4 divided by the total mass flow rate, which is M1. M1 is the total mass flow rate that goes through the system, which is what goes through the pump and the boiler. And if we use that concept, or we use that definition of Y, and the first law of thermo applied to the open feed water heater, knowing that Q is equal to 0 and W is equal to 0, and we divide everything by M1, let's divide everything on the right hand side by M1, so we get M1 over M1 is equal to 1. M4 over M1 is equal to Y, and M7 over M1 is M1 minus M4 over M1, which is 1 minus Y. So this is what we get. This is the application of the first law of thermo and the concept of these proportional mass flow rates. So H1 minus Y times H4 is equal to, or minus 1 minus Y times H7 is equal to 0. So we can calculate that fraction of water taking out of the turbine, directly out of this equation, as the enthalpy of the water at the inlet of the pump minus the enthalpy of the water at the outlet of the open feed water heater minus, or divided by the enthalpy of the water at the extract of the turbine, divided minus the enthalpy of the water at the exit of the feed water heater. H1 minus H7 divided by H4 minus H7. If we know those values, if we know the temperatures at the outlet of the pump, or the temperatures and pressure at the outlet of the pump, the temperature and pressure at the outlet of the open feed water heater, in this case of the outlet of the open feed water heater, we know the pressure, and we know that it's saturated liquid, so this is perfectly defined. And we know the enthalpy of the water that comes out of the intermediate exit of the turbine, or the extract of the turbine. Then we will know what is the proportion of water that went through the open feed water heater that we extracted out of the turbine. If we analyze the entire regenerative Rankine cycle, the work in the high pressure pump is equal to the mass flow rate. Notice that I'm doing all of these in now rate form, not in specific form, because there are different mass flow rates that go through the different elements of the system. The total power going to the high pressure pump is the mass flow rate 1 times the specific work in the high pressure pump, which is specific volume times delta P. The Qn, well, there's only one pass through the boiler, so Qn is delta H from 2 to 3 times M1, which is the mass flow rate going through the boiler. Well, it's actually M2, but it's the same as M1. Now the turbine, if we apply first law of thermo in the turbine, we have two different mass flow rate. So we have M1 times H3 minus H4. H3 is the inlet, H4 is the intermediate outlet. And M5 times H4 minus H5. H4 being the intermediate outlet and H5 being the final outlet. Q out, which is the Q in the condenser, is M5 times the delta H in the condenser. And the work in the low pressure pump is M5, which is the mass flow rate at the final stage of the turbine, times the volumetric flow rate that comes into that pump, which is the same thing as the other volume, not volumetric flow rate, the specific volume. It's liquid water, because what comes out of the condenser is perfectly liquid water. P6 minus P7, the delta P in that pump. So, if we divide everything by M1, and we know that that fraction Y is defined as M4 over M1, it's a fraction of water taken at the intermediate stage of the pump, or of the turbine, compared to the entire water M1, the entire mass flow rate of water M1. We get in specific form that the work in the high pressure pump is V1 times P1 minus P2. The Qn, the cost of fuel, is H3 minus H2. The work in the turbine is H3 minus H4 plus 1 minus Y. It's the fraction at the end of the turbine, H4 minus H5. Q out is the energy release in the condenser. Is 1 minus Y, because that's the proportion of mass flow rate going through the condenser, H6 minus H5. And in the low pressure turbine, the same amount of flow rate times specific volume at 0.6, which is the same thing everywhere because it's liquid water that goes through this pump or this pump, times the delta P from 6 to 7. All right, so now we have enough formulation and enough elements to actually be able to analyze a system of a regenerative Rankine cycle. All right, now let's work out an example that has exactly the same conditions, the same properties, but this time around we are going to use regeneration. We are going to pass an intermediate extract from the turbine through an open feed water heater. But the boiler still produces water at 80 bar and 480 Celsius. We're taking the intermediate exit of the turbine at 7 bar to pass it through an open feed water heater. The condenser pressure is 0.08 bar. So we have the same three pressures as we had in the reheat cycle that we analyzed, 80, 7, and 0.08. The net power output of the cycle is 100 megawatts. So we want this power plant to produce the same amount of power. We're going to see how much water that it needs to pass through it and what kind of efficiency will it yield. First thing we'll determine is the fraction of the total flow extracted for the open feed water heater, the Carnot efficiency, and the thermal efficiency. Notice that I am not including adiabatic efficiencies in the turbine or adiabatic efficiency in the pump or in the pumps. But you can very well add those kind of irreversibilities to the cycle and see how that affects the entire system. All right, so let's start with the summary of the conditions that are given. The open feed water heater operates at 7 bar, which is the exit of the first exit of the turbine, turbine out 1, which is the exit, the first inlet into the open feed water heater, 7 bar. Then it is passed through the pump. The high pressure pump goes from 7 bar to 80 bar. Then at 80 bar is passed through the boiler, where it's superheated to 480 Celsius. The turbine extracts a 7 bar. Then the second outlet of the turbine is 0.08 bar, and it's passed through the condenser. And it's passed through the condenser, and saturated liquid is created, so 0 for quality. And then it's passed through a low pressure turbine, which increases the pressure from 0.08 to 7 bar, ideally isentropic. Also, the exit of the open feed water heater is saturated liquid. This is what goes into the high pressure pump. Okay, so this is a summary of conditions for these regenerative Rankine cycle, and notice that the conditions are identical to the reheat one and the basic Rankine cycle that we analyzed. What we're going to see is what is the increase in efficiency of implementing all these modifications. Is it worth it? So again, let's look at 0.08 bar, where saturation temperature is 41.51. We can use the enthalpy of saturated liquid, 173.88, because that is the exit of the condenser. Saturated liquid at 0.08 bar. And we have the entropy of saturated liquid, 0.5926. At 7 bar, saturated liquid condition, this is the exit of the open feed water heater, 7 bar, temperature will be 165.0, that's saturation temperature. Saturation, the HF or saturated liquid enthalpy is 697.22, and the saturated liquid entropy is 199.22. The superheated condition, at the exit of the boiler, we have 80 bar and 480 Celsius, which yield an enthalpy of 3,348.4 and an entropy of 6.6886. Now we plug all these conditions back into the table. At the inlet of the high pressure pump, pressure 7, temperature is 165. Now notice that what goes to the boiler, before we took saturated liquid water at 41 Celsius. Now we're going to take saturated water, or liquid water, compressed liquid water, at slightly more than 165 into the boiler. So the investment in the boiler is going to be considerably less. Here's the enthalpy and here's the entropy coming into the high pressure pump. Ideally, the pump is an isentropic process. So 1.9922 for entropy transfers into 0.2S. As it exits the boiler, the enthalpy is 3348.4 because we have superheated vapor with an entropy of 6.6586, and that entropy passes through the two outlets of the turbine, the intermediate and the final outlet, because ideally the process in the turbine is an isentropic expansion. Then in 0.6, which is the outlet of the condenser, is saturated liquid at 0.08 bar, temperature 41.51, enthalpy 173.88, and is passed through the low pressure turbine or low pressure pump, ideally an isentropic process in that low pressure pump, so entropy is maintained 0.5926 and 0.5926. Now what we have to do is complete 0.2, 4, and 7, or 2S, 4, 7, and 7S. In order to do so, we're going to look at what the enthalpies and temperatures are in those points, 4S, 5S, and 7S. Let's start with 0.2, which we know is compressed liquid because it is the process of compressing water from 7 bar to 80 bar in a pump. As we know, in a pump, the work can be approximated as specific volume times delta P. Specific volume times delta P is minus 7.3 kilojoules per kilogram. Minus 7.3 kilojoules per kilogram. It's negative, obviously, because it's a compression process in a pump. Now we can use that work, or ideal work, in this equation to calculate the enthalpy at the outlet of the high pressure pump. The enthalpy at the outlet of the high pressure pump is the enthalpy at the inlet minus the work that it requires. Minus is positive, is 704.5 kilojoules per kilogram. That's what comes out of the high pressure pump, and that's what's taken into the boiler. Now in the example before, and the reheat example, or in the basic example, the enthalpy of the water going to the boiler was about 180. Now it's about 700. So it already goes into the boiler with certain enthalpy. That means that we don't have to invest that much fuel in order to heat it. That's the gain and the regenerative cycle. State 4 is the extract. It's the first extraction of water, the fraction of water coming out of the first exit of the turbine, which happens at 7 bar in the same entropy as in state 3, as in the inlet. We see this entropy compared to the entropy of saturated liquid and saturated vapor at 7 bar is somewhere in between, so that means that 0.4S is inside the saturation dome, slightly, almost 99% vapor, 1% liquid. Then we can use that quality to calculate the enthalpy of state 4. Enthalpy of saturated liquid is 697, enthalpy of saturated vapor is 2763. We plug in the quality and we get 2741.87 kilojoules per kilogram. 0.5 is the final exit of the turbine, in which the pressure has been reduced, or the vapor has been expanded to a pressure of 0.08 bar, and the entropy remains the same as in the inlet. We check the entropy of saturated liquid and saturated vapor at that value, and notice that it's in between the two. We calculate the quality at 0.5 is 0.7944. So we're farther into the saturation dome, about 80% vapor, 20% liquid. So we look at the enthalpy of saturated liquid and saturated vapor at 0.08 bar, directly out of the table. We already checked that table. We multiply by that quality and we get 2082.9. That's the enthalpy, the ideal, because we're assuming it has the same entropy. That's the enthalpy of the water coming out of the second exit of the turbine. And finally, state 7S, which is the state coming out of the low pressure pump. This is the pump of the condenser. Right after the condenser, there's a pump that takes the water from 0.08 bar, which is the lowest pressure, to 7 bar, which is the intermediate pressure, so that you can mix it up in the open feed water heater. This pump requires work of 0.692 kilojoules per kilogram. It has that rise in pressure times the specific volume of 10 to the minus 3. Liquid water, remember, always assume has a specific volume of 10 to the minus 3 meter cube per kilogram. Now, using this value, we can calculate the enthalpy at the exit of the low pressure pump, which by first law of thermodynamics is the enthalpy at the inlet minus the work that the pump requires, which is negative. So the water goes into the pump, the low pressure pump, with an enthalpy of 173, and it comes out with an enthalpy of 174. Not much difference because this pump doesn't do much. It just goes from 0.08 bar to 7 bar. So now we can complete that table. We have all the enthalpies in the table, at least the ideal ones. We have the ideal enthalpies. Okay, because we assume that all these processes are isentropic. Now we can calculate the fraction of water Y taking out of the turbine through the intermediate outlet of the turbine, which, according to our analysis, was H1 minus H7 divided by H4 minus H7. Just locate these values in the table, and you'll see that about 20% of the water is extracted at the intermediate outlet in order to mix it up so that it is preheated or regenerated before it goes into the boiler. So water goes into the turbine, 20% comes out of the first exit, and the other 80% comes out of the final exit. That's M5. 1 minus this. Let's do the analysis. The work in the high pressure pump, V1 times the delta P, that's minus 7.3. We already found this. The Q in, which is the investment in fuel, is the enthalpy change in the boiler, which is enthalpy out minus enthalpy in, 2643.9. The work on the turbine, according to the first law analysis, H3 minus H4 plus 1 minus Y, 1 minus the extract, times H4 minus H5. And that yields 1,131.37 kilojoules per kilogram. That's the work and the turbine. And this two-phase turbine. It's not two turbines, but it's a turbine with two outlets. The Q out is the Q in the condenser, which sees about 80% of the flow rate, 1 minus Y, H6 minus H5, 1,520 kilojoules per kilogram. The work in the low pressure pump sees about 80% of the mass flow rate, 1 minus Y, times V6, that's the specific volume at the outlet of the condenser, which is 10 to the minus 3, and we found that to be 0.692, but now when we'll multiply that by the fraction of volume flow rate that it sees, is minus 0.551. So the work, the net amount of specific work, is the work on the turbine plus the work on the high pressure pump plus the work on the low pressure pump, all referenced to their corresponding mass flow rates. But remember, this is in specific form, 1,123.52. And what we're going to calculate now is, what if we want to produce 100 megawatts of power from this power plant? Well, take that 100 megawatts of power divided by the specific work of 1,123.52, and you get 89 kilograms per second of water. So the mass flow rate, the main mass flow rate, that is the mass flow rate going through the boiler, that then is going to be split into one that goes into the open feed water here and one that goes into the condenser, is 89 kilograms per second. The investment in fuel of that mass flow rate times the QN, in specific form 2,643, is 235.32 megawatts. So we produce the same amount of power, but we require less amount of heat. So this is less fuel that needs to be burned in order to increase the energy of the fuel in the boiler, or the energy of the water in the boiler. So now, if we do the analysis, calculate the efficiency of Carnot, doesn't change. The lowest temperature in the system is the same, 41.51 degrees. The highest temperature in the system is the same, 480. The yields and efficiency of Carnot, 58.23%. That's the highest theoretical efficiency that you can achieve in a power cycle like this. But then the actual thermal efficiency is the net amount of work divided by Qn. You can use it in rate form, 100 megawatts divided by 235 megawatts, or you can do it in specific form, 1123.52 kilojoules per kilogram divided by 2643.9 kilojoules per kilogram, or reference to the main mass flow rate. And that is 42.49%. Now, what is the increase? Again, in the basic Rankine cycle we analyzed under the same conditions, we found an efficiency of 39.71%. In the reheat Rankine cycle that we worked out using the same conditions, coming 80 bar and 480 Celsius coming out of the boiler, we found 40.89% efficiency. And now we find an efficiency after regeneration of 42.49. So we've increased the efficiency 1.5% from reheat and another 1.1% from basic Rankine cycle. Is it worth it to increase the efficiency 2 or 3%? Yes, it's huge. Because remember, you're investing 230 or more megawatts of energy of burning fuel to heat this water up in order to create mechanical power, in order to spin a generator. If you save 2% of that, you're talking about 4 or 5 megawatts of power that you'll be saving. Well, multiply that times hour, you got megawatts hour or kilowatts hour, and you know you can correlate that to the cost of electricity. How much is the electricity on your power bill? Check your power bill every month, and you'll see that the cost of electricity, besides the base cost, is maybe, I don't know, 20, depending on the area and the time of the day, maybe 20 cents per kilowatt hour. Okay, so you multiply this by a number of hours, you have so many kilowatts, you have 240,000 kilowatts, you multiply by hours, and you multiply by 20 cents a kilowatt hour, and you'll see what kind of savings you get on a daily basis, what kind of savings do you get on a monthly basis or on a yearly basis. And you'll see that 2% increase in efficiency is huge. It's something that is not only worth it, it is absolutely necessary. So these are the two basic modifications that we are going to study for the Rankine cycle, and these are the types of analysis that you'll be confronted with both in homework assignments and exams. So thank you for your attention, and I'll see you next time.